Hi, everyone. This is Kerim Baran with Solar Academy. I have with me today Jon Bonanno of Strategic Operating Partners, and we are hosting Priya Donti, newly appointed computer science professor at MIT, focusing on AI solutions, specifically for climate issues. And welcome, Priya. Good to have you here.
Thanks for having me.
Well, so Kerim, I think we should start by just putting this question out there, as we always do with Solar Academy. We always put out a question as to what is the purpose of this? And I think the purpose of this is that we have this new artificial intelligence toolbox or process that is possible to apply to climate solutions that may or may not affect certain businesses in our beloved sector. And so I think that we would like to discover, as part of the Solar Academy, teaching others to be empowered. I think that this is really an opportunity where people can learn about these tools or potential tools. How do they apply it? How might it affect their businesses? And, really get off on a good start with this artificial intelligence investigation.
That sounds like a good plan. And Priya, please remember that we launched Solar Academy because, especially in the business world, we've observed that many professionals, especially customer-facing and partner-facing ones, find themselves repeating the same information again and again and again between meetings, between calls, between conferences, and we just wanted to capture it on video and audio so that it can be repeatedly shared in a more efficient way. So whatever you find yourself explaining a lot these days, especially in the last 3 to 5 months with ChatGPT coming live and all sorts of solutions popping up, that would be great to capture those snippets from you that you find yourself repeating in the real world.
All right, so let's jump into the content, and we are very grateful to have Priya Donti here, who, as Kerim mentioned, is a newly appointed professor at Massachusetts Institute of Technology, better known as MIT, and super excited to have her give us a little tutorial on some basic building blocks. And we plan to have more than one session here, so you're not going to run out of content. And Priya, I'll kick it off to you.
Yeah, so I guess to introduce myself a bit more, so I wear two hats. I am the co-founder and executive director of Climate Change AI, which is a global nonprofit that really tries to bring together a community of innovators and practitioners and decision makers to accelerate climate action using AI. And you're going to hear today about various ways what that actually means. In addition, as Jon mentioned, I'm an incoming assistant professor at MIT. And my research focuses on how do you dynamically optimize power grids to foster the integration of variable renewables, and do this in a way that's really cognizant of the data, the sensing that you're seeing on the system, but at the same time is respecting the physics and constraints and all of that good stuff that you really need to make sure that you satisfy in order to not break your power grid. So my work comes in this realm of what's called physics-informed machine learning. How do you bridge machine learning and data-driven techniques with the physical and engineering knowledge we already have to try to get the best of both worlds?
That is an incredibly good topic, and I encourage all of our viewers to also access the sessions we did with Ted Thomas around untangling the grid, because not only is this a physics and an energy problem, but it's also a politics and policy problem. So we encourage people to go take a look at those sessions we did with Ted, and the upcoming sessions we're going to do with some FERC chair people coming up soon, but not ready yet. So Priya, this is a very, very time-sensitive, on-point conversation. Please lead.
Yeah, absolutely. And I mean, I know that kind of AI has come into the public consciousness, in a huge way over recent weeks because of in particular, ChatGPT and other similar models. But in some sense, actually, the story of AI, is not new. AI was invented back in the 1950s and actually started not with machine learning techniques, but with symbolic techniques. Basically, can I write down a set of rules that describe the problem I'm trying to solve? For example, the game of chess. Can I just write down what the rules of chess are and find some algorithm that's able to reason over those rules in order to do something. So back in like 97, Deep Blue, for example, was an AI agent that actually beat, the world's greatest chess players on this topic. But since then, especially in the last few years, machine learning has become a kind of predominant paradigm. And machine learning is the techniques that learn from data, large amounts of data. And machine learning has been around for a bit as well. I mean, Siri in your smartphone kind of in the last 10 years is powered by machine learning. There were some advancements, in the last 5 years about machine learning being used to achieve superhuman performance on games like Dota 2, or help solve the 50-year-old protein folding problem, the AlphaFold innovation, and then of course all of the things we're seeing with GPT, Bard, and DALL-E. So maybe given that history, what I wanted to do is just start in and dive in with some definitions, really just talk about what is machine learning, what are the different types of machine learning, and then maybe get into what that actually means for kind of energy systems in the clean economy. So I think that's my cue to start sharing slides.
That is, and we will have these slides associated below in the links, so you'll be able to access these slides as well. So do not worry.
And Priya, will you also speak to, maybe not today, but in a future session, the relationship between machine learning and AI, and how what's the break-off, and what are the different use cases for these different approaches?
Yeah, so I think that's actually a great preemption for my first slide here. So yeah, so what is machine learning? And exactly, when we talk about machine learning, we do want to talk about what artificial intelligence is first. So artificial intelligence really refers to any algorithm that allows a computer to perform a complex task. Sometimes these are tasks that we associate with human intelligence, so speech or reasoning or vision. But sometimes they're not, right? Machine learning and AI are used to predict solar power output. That's not canonically something a human would do. So really, it's just any task that's a complex task. And as I mentioned, kind of initially when AI started, it really was about just writing down a formal set of rules and figuring out some way to reason over those sets of rules. But today, we've seen a huge surge in machine learning, and machine learning is a subset of artificial intelligence. And it specifically refers to techniques that automatically extract patterns from data, and usually large amounts of data. And so because machine learning has become such a kind of dominant paradigm within AI, you'll actually hear these terms used interchangeably quite often, and I'll do that often as well, kind of interchangeably use AI and machine learning. But AI is actually a bit of a broader concept that encompasses symbolic techniques, other kinds of techniques like physics-informed techniques, things like that. Whereas machine learning is specifically kind of data-driven analysis, automatic data-driven.
So can I ask you a layman's question? So for example, think of a big insurance company with all the data that they have access to, all sorts of things that they insure and things that go wrong, and like the analysis of their data set to figure out how to price their premiums and how to, create their products. I assume that would be using more of a machine learning subset of technology rather than, I guess we wouldn't call that artificial intelligence. But when I do ask a question to ChatGPT and get a page of text as answer, I mean, it could be analyzing a key character from a play, and is that called artificial intelligence?
Yeah, so I'd say both of those things are machine learning, and as a result, both of them are also artificial intelligence, in the sense that even GPT, and I'm sure we'll get into this more later on, all it's doing is analyzing some structure in its underlying data and parroting that back out. So there's actually this famous paper, Stochastic Parrots, which describes these kinds of models as basically models that really try to understand or analyze or learn some kind of structure or pattern in the underlying data. And then with some random probability distribution, basically just spit something out that looks kind of like that. And so that, even though it seems more intelligent on the other side, it's actually not inherently any more intelligent than just doing large scale analysis of your insurance data. It's actually something very similar under the hood.
Got it. They are kind of making it look like it's different, like it could be different every time you ask the question. I guess there's some sort of variable in there that causes it to come slightly different every time.
Yeah, and that's just the stochastic in stochastic parrots.
Right,
Basically,
exactly.
as you put in certain kinds of data, there is some kind of randomness in terms of kind of what spits out.
Yeah, makes
But
sense.
Kerim, you've raised a good, very climate solutions focused solution, which is insurance, because with increases in extreme weather, you're going to have new underwriting requirements.
But that takes me to the parroting word that Priya just mentioned, because each extreme event is more extreme than the previous. At least it seems so in our
Right. So
lifetime.
looking exclusively at historic data is not going to work. So you have to take the next step, which is predictive.
Right. And how
Yes,
accurate is
exactly.
that going to be? So are those coming out accurate? I guess is the question.
Exactly. And that is the real question. And this is where this kind of, area of kind of physics informed or knowledge informed machine learning comes into play. So for example, if you're an insurance company that's trying to predict what climate risk will look like in the future, one thing you could do is just try to learn from your current weather data using a machine learning model and predict that out. But as you're observing, because the data you're learning from is fundamentally different than sort of the situation going forward, you're not going to get that. But what people have done is do things like say, I have a climate model that has my physics written down, but there are some parameters in there where I don't know what the exact value should be. And so can I actually use data to inform what the parameters of my climate model are? And that climate model, it's the physics that will continue to persist. That climate model can actually generalize and make predictions we can trust in the future. So I'm increasingly a big fan of these, knowledge, domain informed, physics informed, knowledge informed approaches, as opposed to just scraping a bunch of random data from the internet and hoping something emerges from that.
Yeah. Sounds good. All right, please continue.
Yeah. So yeah, and I did want to get into, and I think some of our discussion has already started here, kind of when we say machine learning, in some sense, the core concept is, again, very simple, automatically analyzing large amounts of data. But this actually plays out in a couple of different ways. And so there are kind of three major paradigms for machine learning. So supervised learning, unsupervised learning, and reinforcement learning. And I want to talk about each of those in turn. So supervised learning is a situation where you have a fixed data set that has labels or answers on it, and you're trying to learn some relationship between your raw data and the answers that you have labeled on it. So really maybe easy to grasp, hopefully, example there is if you have a ton of images, each of which is labeled dog or cat, you can imagine a machine learning algorithm trying to figure out, okay, I'm getting as input the raw pixels of the image. I'm analyzing something about it. I'm making some kind of guess. And at the other side, I'm being told, am I right or am I wrong? Is it a dog or is it a cat? And then through kind of iterative feedback, continuing to try to make those guesses and updating its parameters based on the kind of signal on the other side as to whether it was right or wrong, the machine learning algorithm gradually learns how to basically learn this mapping from an image to your label of dog or cat. One way to think about kind of supervised learning tasks is these are situations where a human could do exactly what the machine learning model is doing and probably better. I trust myself.
Mechanical of Amazon, for instance.
Yeah, or like me, right? Like, I mean, I trust myself in some sense to look at an image and tell you if it's a dog or a cat, except in maybe edge cases where there's some species that look kind of similar. I can pretty confidently tell you I'll be able to do that. Your machine learning algorithm may be wrong every now and then, but your machine learning algorithm can do it at much greater scale. I can't label 100 million images for you. A machine learning algorithm can. And so supervised learning is really where you want an algorithm to do something at scale that a human could do, but where you're okay with it being done slightly worse because of the scale.
But in all cases, supervised learning always includes a human or does not include a human.
So it involves a human to actually create your data set. So you do have to make sure that, yeah, you have the ability to have a clean data set where you have already established what the labels are. Mm-hmm. And once your machine learning algorithm learns from that, it can now take an image that is similar to what it's already seen, but is not exactly what it's already seen and map there. And so this really, brings up really important questions about, well, how do you get a massively labeled data set who is able to label that? Where does the labor come from? Under what conditions is the labor coming? And what's the pay around that?
And where does
There's
that
a lot that comes
intellectual property, and where does that intellectual property reside? Like all that labor is capital investment. So who owns that too?
Exactly. And these are kind of, important and open questions. I mean, this comes up with GPT, which is not an instance of supervised learning, and I'll get to that, but even just in other settings where you have large amounts of data that are being analyzed for input to a machine learning model, kind of how do you deal with the IP behind those images, especially depending on, if the outputs that turn out on the other side are really deeply informed by the data that went in. So these are all really important and not open in the sense that, there are people who have studied these questions, but I think it's high time that we kind of bring any of those theories into practice at this point.
Would you say the internet at large, being basically servers worldwide with information at the edge in most cases, is most of that labeled data sets? Would you say that's mostly labeled data sets or not labeled data sets?
I would say that's not labeled data sets.
Okay.
And,
so you're really talking about a labeled data set example would be something like satellite images captured by X company that says, this is a rooftop that has X amount of irradiation on it. It's at Southwest, blah, 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 this triangulation, et cetera. That would be a labeled data set, but it would also be considered a closed data set, right?
Yeah, so that would be a labeled data set, and a labeled data set doesn't, inherently necessarily have to be closed or open. This is where sort of data sharing policies and things come into play. So in the academic community, there are actually some common, what we call benchmark data sets, where they are open for the community to use. But then additionally, again, it does take a lot of resources and both, equipment resources and human resources and expertise to really get these data sets together. And it does mean that entities that collect them are often those with the most power and finances in society. And then they also often have an incentive to keep them proprietary because they want to generate value from them in some way that others can't. So a lot of stuff to do there with incentives and how we really open up the landscape. Yeah, but then kind of getting at this point of, is the data online, labeled or not? It's not. And in some sense, the vast majority of data we have in the world is not labeled. And so there's actually another branch of machine learning called unsupervised learning, which really deals with, in a case where you don't have answers about your data set, is there still some way that you can learn some underlying structure in your data set and use your knowledge of that structure to do something? So one example is clustering. So if you have a bunch of images and you don't know what they are, you could still try to figure out some machine learning algorithm that sorts images into buckets based on which images are the most similar to each other. And then maybe a human can go later on and say, oh, that's the cat cluster and that's the dog cluster or something like that. But the algorithm doesn't know that. It's not able to assign semantic meaning or anything like that to that cluster. It just knows that those things are similar. And even though it's not shown on this kind of base image, which I don't have an attribution for it because it actually pops up everywhere on the internet without attribution. So apologies to whoever the original creator is. But generative AI is a type of unsupervised learning, where basically you're asking your model to take in a data set, in the case of GPT, the internet, and learn something about the structure. So what does a coherent sentence look like? And then when prompted, spit out something that fits what the model thinks a coherent sentence looks like. And I'm using the word coherent, specifically to mean it's not a truthful sentence. It's not necessarily a quality sentence. It's a sentence that matches the linguistic patterns that we see on the internet. So GPT is basically doing next word prediction. So it's saying, I have this data set of the internet. If I see a certain set of words, I know from my data what word is usually next. So let me just figure out when I see a particular sentence, what word is next, and just try to generate something like that for you. But again, there's nothing inherently encoded in there about kind of truth or knowledge. It is really parroting what it thinks it sees in the underlying data set.
You've mentioned a couple times images so I assume video and still images, but also words. And I assume that between supervised and unsupervised learning, they're both equally similar in terms of an image or a video or words. Is that right?
Yeah, so the
Okay.
general kind of paradigm, you can kind of, it applies to kind of any kind of input data, be that exactly like images or words or physics data or anything like that.
Numbers or
or
something.
Numbers.
mathematical statements and equations.
Mm.
Yes.
Yeah. So in principle, you can any of those things. In practice, some of those problems are harder than others. Getting a machine learning model to output the correct answers to mathematical questions is harder to do from raw data than other things. And in part because we're less forgiving if an output is wrong. If an image is a little bit blurry in the machine learning output, we tend to be like, okay, but it still looks pretty real. If a math problem is a little bit wrong, it's wrong. So there's an extent to which our evaluation of these things also affects how we feel about the inaccuracies in the output.
Yeah, you've underwritten the home in Florida just a slight bit off. Your insurance policy is underwater, literally.
Exactly. So yeah, this general question of thinking about what is a sort of critical setting where we really need to trust the output versus one where we're okay with it being a little bit wrong. These are very different sets of settings, and the way we should think about using machine learning in those settings is truly different. Yeah, so maybe jumping into the third branch of machine learning, or a third branch. This is there are things that fall out of this taxonomy, but both supervised learning and unsupervised learning deal with, in some sense or the other, look at a fixed data set and learn something about it. There's another category called reinforcement learning, which basically involves training a machine learning model that's interacting with some kind of quote unquote environment. So this could be like a physics engine, this could be a power grid, this could be like a game engine for a multiplayer online game. But what your model is doing is it's trying to take some actions on that environment. So in the case of a game, what should the player do? The model might be trying to learn some kind of policy for how to take actions for that player. Or if you're trying to learn how a battery should charge or discharge on your power grid, then the action might be, how much should I charge or discharge? And what the machine learning model does is it tries an action. It gets feedback from the environment about how good that action was. So, in the case of the battery, how much money did I make? Did I destabilize the grid? And then based on that, it updates its underlying kind of parameters, that what's enabling it to generate its recommendation for what action you should take. And it just does that over and over again, tries to take some kind of action, gets some feedback, and does that over and over again. And so that's reinforcement learning. And in a lot of cases where we're talking about optimizing a heating or cooling system, or optimizing a power grid or something like that, something where you're actually trying to think about what are the actions that we should be taking in an automated way, you're often talking about reinforcement learning or something similar.
That's incredibly helpful when you look at the triangulation of just energy storage assets. For example, you've given the example, but also the state of charge of the battery itself, the operation of that battery in the most optimal manner so that you're not degrading it over the period of time that you care about financially. But how does it respond to the grid? What was your outcome financially? All that. I mean, it's just like an enormously complex set of information. And to have a reinforcement learning, what would you call it? Tool, agent? Mm-hmm. How do people characterize these in actual practice?
Yeah, so you'd call it a reinforcement learning agent, exactly.
Okay.
But tool also works depending on sort of whether it's the whole solution or a part of it.
Okay.
Yeah, and so I think these can be incredibly helpful. There are some caveats. One is that you often need either a real system you can test on or a simulated environment that is, realistic enough that you have some confidence that if your agent is learning to do something on your simulated system, that it actually tells you something about how the agent would behave on your real system.
And how long do you think that takes? Let's say it's a qualified team with real assets, and they're going to do a parallel practice. They'll have a practice system that's really not connected to anything that could hurt. And then you have a real system that you're just running, and some person is sitting there going, okay, on, off, on, doing it manually. What would be the timing? Is this like 2 weeks? Is it 15 years? When do you think people can get enough confidence with this reinforcement learning element agent to let it go?
Yeah, I mean, I think it can be a matter of years, and in some sense, it has to be, in the sense that we do just really need to be dynamically optimizing power grids to be responsive to, higher renewables integration. But there's work to be done if we really want to realize that time scale. So these realistic simulators, for example, don't exist. And there are efforts to build, quote unquote, digital twins of the overall power grid, which is, really a real-time snapshot of what your power grid is doing. But I would say that's a solution for reinforcement learning algorithms that have already advanced along the readiness pipeline enough that you're in that last stage of testing. We don't even have kind of simpler simulation environments that are not pulling in all your real-time data, but where a power system operator, for example, has sat down and agreed, this is reflecting how my grid would actually work, what kinds of anomalies or intricacies I would actually see during actual practice. We need even that just basic simulation infrastructure along with agreed upon metrics so that if your method succeeds on the simulation infrastructure, you know what success means and you know what's next in order to test it out. And the other thing is reinforcement learning methods, they have achieved really powerful performance in the last years, but they can fail and potentially catastrophically in unexpected ways. And so bringing back this theme of, physics-informed or domain-informed learning, there's some work, including my own, that really tries to bring together concepts from robust control and control theory, where you can actually prove something about what your controller is doing with reinforcement learning so that you're not just depending on seeing in real life how your algorithm performs and kind of crossing your fingers that it won't break anything or hoping, making your best guess, but really can you actually provably say something based on the mathematics of the system about what kinds of failures you know won't happen?
I've got 2 questions here, which is you have direct experience at a major transmission and distribution company. I'm not going to name their name, but how insightful are they on this topic of reinforcement learning? Because this would seem like a very amazing tool for someone that owns transmission and distribution assets.
Can I add one more thing to that? Before they get to the reinforcement learning or deploying the reinforcement learning agent, how long do they have to do supervised learning or unsupervised? Do they even do unsupervised learning in the context of a power utility company?
It's a great question. So I would say that often, you would use supervised to unsupervised to reinforcement learning. It's not that it's exactly a progression. They're paradigms that solve different problems. So if you want to do something like predict how much solar power output you're going to get from your solar panel based on the weather and time of day and all of that, then that's pretty, nicely framed as a supervised learning problem where you have some information about your historical weather, historical inputs, and then your solar power output, and you can just map between them. Yeah. But then the question is, if I have a prediction, what do I do with it? What action do I take? Sure. And that is not something that, supervised learning or unsupervised learning canonically would solve. That is just canonically a reinforcement learning problem where you're trying to learn some kind of action. Yeah. So these algorithms
do you bring on the peaker plant or not? I mean, that's
exactly.
Yeah,
and these algorithms do kind of, interplay with each other, but they don't have to. In some sense, I could produce a manual prediction of solar power output, and that would still be a reasonable input to my reinforcement learning algorithm in order to do something automated. So yeah, they solve slightly different problems. And Jon, to your question about, the readiness, I guess, of different system operators, I would say that because these things solve different problems and because the input technologies or the situation around the availability of data and simulators is very different for these, I would say that many power system operators actually very widely use machine learning for what I would call situational awareness problems. So I want to know what my solar power output will look like. I want to know what the state of my system looks like, because I want to know leads somebody to be able to take an action in a way that the system operator views as being trustworthy based on that information. Whereas reinforcement learning is very much about having the machine learning algorithm itself take some kind of action And there's, understandably more hesitance around that because you really can break your power grid if you do something wrong. And so one kind of publicly available challenge is actually by RTE France. They run a public challenge called Learning to Run a Power Network, or L2RPN. They've actually created some basic simulation environments that try to reflect some of the realities that the French system operator is seeing on their power grid, and basically kind of present that as a challenge to the machine learning community to say, can you come up with a reinforcement learning agent that either, automatically, or in some of their challenges in a human in the loop way, is able to come up with good actions that we can actually take on our grid.
At 80% nuclear, it's an easier problem to solve.
Got to start somewhere.
Totally agree. But this reminds me also, this simulation requirement, like these environments, it reminds me a lot of the late 90s where, mobile phones were just kind of becoming very, very, very popular at the time. And everyone was trying to do apps on these mobile phones. But of course, the mobile phone companies and the carriers didn't want you to play with live ammunition. They didn't want you on the real devices right out of the gate. Now, very different problem if your phone crashes than if the power grid crashes. So I can understand the level of safety and reliability is very, very different. But it seems like there's a place in this new world for power simulation environments where people can test their tools safely, and it can raise awareness and trust of these transmission and distribution owners. So there's a whole business probably in just making simulation elements or environments. Is that right?
Yeah, absolutely. And I think that the challenge is, I think there's a lot of utility and value, utility in the sense of usefulness as opposed to power utilities. There's a lot of value in making these kinds of simulation environments available. But it's the classic problem that comes when you look at the startup landscape. Everybody wants to build the things that create profit and value on top of infrastructure that already exists. Often you have some kind of, public goods issue when it comes to actually building the infrastructure that everybody can build off of. And so I think clever business models can help with this, but I also think that this is a place where public funding and public-private partnerships can really play a huge role in kickstarting this.
So Department of Energy, EPRI, universities, these kind of places are the place to incubate these kind of environments to test this stuff. You think that's the best place?
Yeah,
Okay.
and I think, again, in collaboration with startups and others who would be the users on the other side. I think you don't know if a system is useful until you actually try to use it. And I think knowing that sooner rather than later, even in the early stages of development of these kinds of systems, is incredibly important.
Fantastic.
Yeah. So maybe zooming back out, getting at some of the questions you asked earlier, John, about, images and videos and text and all of these things, right? How do they play into these different paradigms? So I wanted to actually slice the kind of machine learning world in a couple of other ways. So I talked about this, what kinds of use cases or what kinds of data or environment do you have? And that's the supervised versus unsupervised versus reinforcement learning paradigm. But there are also different kinds of machine learning models. So for each of these paradigms, there are different models that you're using to somehow map between your data and whatever output you want. And these models can be used within supervised or unsupervised or reinforcement learning, but you basically are trying to just figure out what is the actual engine that's mapping between my inputs and outputs. And so one that often comes up, right, and I think is very present in people's minds, is artificial neural networks, also known as neural networks, and then when you hear the word deep learning, it just means a machine learning paradigm that's using artificial neural networks. And they're called artificial neural networks because they're loosely inspired by the neural networks in our actual brains. I will say very loosely, and there's sort of genuine debate about how real that connection is. But if you hear neural networks or artificial neural networks or deep learning, they're roughly referring to the same thing.
At the least, it's good marketing.
Yes, it's great marketing. But also there are lots of others. So, deep learning is not the only type of model, or, neural networks are not the only type of model. There are things like support vector machines and decision trees and Bayesian models and so forth. And I'm not going to get into the details there. But what's important to know is if you want to use machine learning, you don't have to use deep learning. There are often other models you can use, and some of these are really simple to implement. There are open libraries in Python, for example, scikit-learn, where you can, in just a couple of lines of code, spin up a support vector machine or a decision tree or something like that. So some of these earlier models are more accessible than one might think. And in a lot of practical settings where your underlying data is imperfect or noisy, right? I've talked about all of these situations where you need a perfect data set to do something, but in a lot of situations where data is imperfect or noisy or something like that, we have seen often these simple models do quite well, whereas the more complicated models are maybe more brittle to these kinds of things, or otherwise just need kind of additional research before they're perfect in those real settings.
And are most of these open source right now, or are there private companies building such models as well?
Yeah, so the frameworks to create the models are largely open source. So scikit-learn, I mentioned one, but then also TensorFlow, PyTorch, and JAX are popular frameworks to be able to code up your own, your own deep learning algorithms. The models themselves, when a company creates a model and trains it for some kind of purpose, is the model itself often public? Often no. In the research world, yes. But I mean, for example, GPT, not a publicly available model. And this has all sorts of implications for who can actually build on it and who is able to audit it to really understand what's going on under the hood and what needs to be improved from a public perspective.
Right.
But you mentioned something that was important there. So most of the model work and the way you're implementing this stuff is done through Python programming language. So if someone was, say, at a technical school right now and listening to this and saying, hey, this sounds super interesting. How do I begin maybe learning Python as an entry point to be productive here? Is that right?
Absolutely. So Python, and some people are starting to prefer, Julia, another open source language, but Python is a great kind of entry point into this. And again, I think it's one of those things like the Python language itself is open and these frameworks on top of it are open. It really is a situation where a lot of people can just get going with these.
Okay, good. Thank you.
Yeah. And then, I guess the last, taxonomization I wanted to provide here is that, machine learning models can take in different kinds of data. So you can have supervised, unsupervised reinforcement learning. So different settings, you can have a different model in those settings that's mapping from the data to the outputs, but then what does the data itself look like? And there are a couple of kind of terms you might hear in the world that and what these terms are doing is really describing what is the data at hand. So if you hear the term computer vision, it's referring to a situation where your input or your output is images or videos. If you hear natural language processing, it means that your input or output is, text or speech or natural language of some sort. And if you hear robotics, it just basically means that you're trying to enable some kind of embodied agent to move around or do something in the real world. And so your inputs and outputs are often physical data or sensory data of some other sort.
Is there a special data case for math or for some sort of arithmetic or type of situation?
It's a great question. I haven't heard sort of a keyword for it. That doesn't mean one doesn't exist, but there isn't, as far as I know, like mathematical processing as a particular use case.
Got it.
And I think partially this is historical, just what data sets exist have been easily, readily centered as benchmarks in the machine learning community.
Well, a company that I've worked with is doing computer vision around transmission and distribution assets, and they capture helicopter videos of these remote assets and drone videos and pictures, et cetera. And then only a tiny, tiny percentage of it is analyzed by humans because it's overwhelming. And we have clearly not done a fantastic job at upkeep and operation and maintenance of this infrastructure. And so having the ability to, as you say, 15 of these images you could probably do, but 15 billion, that would be hard. But this might be a great application set for it.
Absolutely. Yeah. And this is one where, that use case of just, predicting outages in transmission distribution infrastructure, doing vegetation management. Buzz is doing it, EPRI is doing it, and there are a bunch of others. And this is, I think, just like a really incredible use case for machine learning. Yeah.
What are some other use cases?
Yeah. So I'm happy to jump into that part if you'd like, actually.
No, let's hold off.
That's a good heading there. Strengths and weaknesses. Let's go.
All right.
But let's not jump into immediate, because the next session I think we'll do is here's a practical example of applying some of this stuff.
Okay.
So
yeah, absolutely. And I think if we have time today, I'll try to give the like high level quick taxonomy teaser to kind of to try to provide a groundwork for that. But then, before that, let's definitely dive into the machine learning strengths and weaknesses. All right. And I think we've talked about a lot of these. So strengths, machine learning is good at performing tasks at scale. So again, scaling human intuition in order to do something at scale may be slightly less quality than a human would have done it, but at scale. Another one is optimizing complex systems. And this is related to this idea of reinforcement learning that I mentioned before, really taking in data and other information about your system and being able to provide some notion of, what are the actions you should take and really learn that in a really nuanced way. Another one is creating derived data. So taking, for example, large amounts of satellite imagery and really trying to extract from that, where are the solar panels in the image, or trying to take large amounts of text documents and really extract from that, what are the policy commonalities in different policy texts that we see that enable us to, understand what those patterns are to make new policy, or analyze large amounts of patent data to understand what the patterns are. So really taking large and raw amounts of data and trying to distill it some way into an actionable insight. And then another is, dealing with different kinds of data sources. So for example, forecasting solar power output, which is an example I brought up a few times, it's something that we've been doing forever, right? First using rule-based techniques where you basically write down, is it a holiday? Is it, what day is it? And, I guess a holiday doesn't matter for solar power output as much as, say, a power demand, but you get the idea. You write down some kinds of rules. And you predict these things, or you can use physical numerical weather prediction models to come up with what is the solar irradiation going to look like somewhere, and what does that mean for solar power output. But what machine learning is really good at is taking in multiple types of data and really learning to analyze patterns among that. So you could have a machine learning algorithm that takes in historical weather data, but also takes in the outputs of a numerical weather prediction model. And it also takes in images of clouds moving overhead, your solar panels, and really analyzes all of that together in order to provide some kind of prediction. So this idea of just dealing with many different types of data sources and finding really powerful correlations between them is something machine learning is good at. All right, so what's it bad at, or what are its limitations? So one, as we've talked about, very data hungry. So you often are in a situation where you're needing to label or collate a huge data set, and that often means either you are needing to put a lot of financial and human resources into that, or you're settling for lower quality data. And if you're settling for lower quality data, it's important to understand this principle of garbage in, garbage out. Since machine learning is trying to analyze patterns in its data, if the patterns and the data are garbage, it's going to output garbage.
Wait a minute, let me pause there for a second. So you're saying that if the data is unlabeled, then we're moving over to the unsupervised side. Mm-hmm. And we're just going to get lower quality outputs because of that. But then some folks are saying, I'd like to improve the quality of the data by doing what? You said something earlier at the beginning of what we were discussing here, that in some cases people are doing, I don't know, it was sort of, maybe it was I imagine this word, but less substandard conditions where people are doing certain types of work. What are you finding in the world of artificial intelligence? Are people in like sweatshops in some place that they're just sitting there like for 16 hours a day saying, this is a dog, this is a dog, this is a cat, this is a dog?
Yeah, so two things I'll bring up there. So unsupervised data doesn't necessarily mean it's worse data. It's a different task. What is worse data is sort of if you don't know what your model is seeing. So if you're scraping the entirety of the internet, there's hate speech on there. There's all sorts of stuff in there that your model is seeing. And that's very different than if you're curating an unsupervised data set, not because you know the mapping between the data and answers, but just because you know what is in your data, that there isn't hate speech in there. That can be a form of ensuring quality. Now, yeah, and labor is an issue. I think, you know, Mechanical Turk is often used to label data sets, and there are, of course, like various ethical considerations with that. And then when it comes to, you know, GPT,
open that up a little bit further. Mechanical Turk is, we explain, go a bit further with that. Explain that, because
yeah, so Amazon Mechanical Turk is basically a system where you can farm out really quick tasks to a bunch of people, and they get paid a small amount of money for each task that they complete. And it's a way for people to potentially make sort of some marginal additional income to do things like data labeling, sort of in the same way you sometimes get incentivized to, I don't know, provide reviews on Google or something like that. But in a situation where people are depending on that for their livelihood, maybe they're having trouble finding other work, it doesn't necessarily pay enough for that. And it also, of course, takes away time from things like finding other work. So they're just, people are not paid enough for this, basically, even though it's providing a ton of value.
Thank you. Sorry for
no,
going too far on that.
absolutely. And then with GPT and OpenAI, there were some breaking stories about the fact that there was a lot of kind of data labeling and content labeling going on in, I believe, Kenya, where workers were not necessarily being paid even what locally would be potentially an acceptable wage. And so it's super, work on data is extremely undervalued in the sense that the algorithmic work is often viewed as flashier than that, but work on data is just essential for making sure any of this algorithmic work actually means anything.
Okay, thank you.
Yeah. All right. The other thing is machine learning can be biased, and in a couple of ways. So one is in terms of the patterns in the underlying data. So for example, a common use case of machine learning, or one that is kind of worked on in the climate change space, is that you would analyze data on buildings, so sensor data or something like that, in order to understand which buildings are more likely to be successful candidates for a retrofit. That's great, right? It's a great way to kind of try to pinpoint your retrofits so that you're doing it in places that it counts. But it's also worth noting that buildings data in the US, for example, reflects the histories of redlining and racial discrimination in the US housing sector, where different parts of the building stock have been invested in differently over the years. And so those biases, even though it's data on buildings, it's this engineering data, right? It reflects human histories and social and political histories that then when you analyze that data are there, and your machine learning algorithm is going to pick up on those patterns and replicate them because its output is fundamentally following the patterns that are already in the data. And so that's something that's just, it's extremely important to be cognizant of just what is your data really encoding? And is that something you actually want reflected in the output? But it's not just the data. It's also about what we choose to use machine learning for. So what use cases? For example, there's a lot more machine learning right now in precision agriculture than there is for smallholder farmers. That doesn't necessarily mean that the use cases are differentially impactful or anything like that. It's just a question of, who decided to do it and who had the resources to do it. Or, in a non-climate example, when it comes to policing, machine learning has been used in areas like predictive policing, where the goal is to predict who will commit a crime or where a crime will be committed based on past data. And it's not just that the data is biased, because what you're often seeing is data on arrests rather than crime, and arrests are correlated with where we choose to dispatch police resources in the first place. But it's also the case that the kinds of crimes that are predicted, it's not often financial crime on Wall Street, nor is it abuses by police officers themselves. It's often, the crime that is being predicted is crime by populations with less power in society. So the ways in which we really think about what machine learning is an accelerator of the systems it's used in, what systems are we using it in? That's not a neutral choice. We're often making very powerful choices about where machine learning is actually helping us accelerate something in society.
This is such a great point, because I think that a lot of, over the last, say, 24 to 36 months, a lot of companies and organization leaders have made a concerted effort in hiring sort of the less obvious candidates for engineering work in clean economy or sales, marketing, whatever it might be. And it sort of immediately surfaces the fact that STEM learning in elementary school in less privileged zip codes is really quite poor. And so you don't find a lot of mechanical, electrical, computer science engineers coming out of these types of neighborhoods or communities. And so there are just less candidates available. And so you have to be incredibly intentional about your outreach. But in some cases, the pool is just not very deep. And so you're saying, well, okay, candidate to candidate, how do I do this, and do it for the best of my stakeholders in my organization? Your point here is really great, which is the data itself could be corrupt before you get it. And so like our system around education in STEM is already 10 years behind. So how are we going to fix that today? It's really hard.
Yeah, and it requires a combination of investing in the systemic solution, right? Making sure that we are investing in, for example, early education, but also, of course, being aware of biases that might be preventing us from even getting the pool of candidates that's out there. The way we specify various criteria, are we requiring a degree for something that doesn't actually need a degree from a skills standpoint? And this kind of thinking, right? This intuition about just how do you make sure that you're hiring in a way that's equitable, that's cognizant of the biases in a broader systemic sense and in your own process? That kind of thinking applies directly to when you're thinking about machine learning workflows. It's in some sense no different. You want to think about what is the system the algorithm is operating in, what are the specific choices I'm making when designing it, and what are the specific choices or things encoded in the data it's getting, and really thinking about that holistically.
Such a good point.
Yeah. All right. And then the last two things here are maybe obvious, but I think worth saying anyway, or things we've covered. So one is that machine learning assumes that patterns are persistent. So if it's seeing a data set, it assumes that data set is the world. And if you try to get it to predict for a different world that is not reflected in the data set, it's not going to do it. And so this is exactly the example from before of if you're trying to predict long-term weather under a changing climate, your historical weather data isn't going to be distributed the same as your future weather data, and you need to do other things to deal with that. And then fundamentally, machine learning is statistics. And with statistics, we all know that phrase, correlation it's finding correlation, it's not finding causation. And machine learning is similar. You're finding how things are related to each other or correlated with each other in the data. In order to find kind of causal explainability, you often have to do analysis that is not just basically data crunching or number crunching to understand that.
Wow. This is a great start for beginning to understand this incredibly important and complex topic. I really want to thank now Professor Priya Donti. Last time I saw her here in Sonoma County, it was not Professor, I don't believe. So now congratulations are in order. But this has been a fantastic Solar Academy Suncast episode of learning just the beginning of what I hope to be a long number of series and ongoing about this subject of artificial intelligence and climate solutions, but also we're going to be dissecting certain company examples of how people are using these tools effectively. I am super grateful to have you on as a guest, and we look forward to very soon having you again. Kerim, you want to sign off?
Thank you very much, Priya. This was very useful, and I really look forward to going into this use cases in different sectors of climate in the climate sector, as well as many other use cases. So
fantastic. Looking forward to it.
Having you on.